Think about the last time you streamed a high-definition video or played a fast-paced online game. To your computer, that data is just a perfect, crisp sequence of digital ones and zeros, a flawless square wave traveling through space. But out here in the physical world, distance is a silent killer. As a signal travels, it fights a losing battle against nature. It warps, it loses power, and it melts into a chaotic mess of analog noise. If left unchecked, our digital world would simply collapse into static over long distances. So, how do engineers protect our data from disintegrating? The answer lies inside a brilliant piece of everyday engineering, the coaxial cable. Unlike a standard electrical wire, a coax cable is built like a fortress to shield data. At the absolute center sits a solid copper core, carrying the high-frequency signal. Surrounding it is a thick white dielectric insulator, keeping the signal contained. Next comes a crucial line of defense, a tightly woven, braided metallic shield that acts as a barrier, deflecting outside electromagnetic interference. Finally, a durable PVC outer jacket seals the entire system. But this physical design isn't just for durability, it's built to conquer a harsh law of physics. You see, high-frequency signals don't travel through the middle of a wire because of a phenomenon known as the skin effect. Alternating currents crowd along the very outer surface, or the skin, of the conductor. As the frequency climbs into the gigahertz range, the usable area of the copper shrinks. This forces the signal to fight massive resistance, creating an exponential drop-off curve known as attenuation. The higher your signal's frequency, the faster the cable saps its energy. To minimize this loss, every single millimeter of the cable's geometry must be perfectly balanced. But resistance isn't the only enemy. Electrical paths have a property called characteristic impedance, measured in ohms. Think of it like a smooth highway for waves. If a wave traveling down a 50 ohm connection suddenly hits a 75 ohm junction, it encounters an abrupt structural barrier, an impedance mismatch. Instead of passing through cleanly, the wave splits. While some energy transfers forward, a massive portion of the signal literally bounces backward, creating a reflected wave that crashes directly into your incoming data, causing severe distortion. This is why precision engineering matters. By meticulously matching the impedance of the transmitter, the cable, and the receiver to a universal standard, like 50 or 75 ohms, reflections drop to zero. The chaotic, distorted waveform is instantly rectified back into a clean, stable, optimized transmission. It is a seamless harmony of physical hardware design and wave physics, quietly keeping our digital world connected. If your cable's characteristic impedance doesn't perfectly match your antenna, that energy won't travel to the path cleanly. Instead, it violently reflects straight back down the wire, creating dangerous voltage standing waves that can damage your hardware.